What if the first travelers through a wormhole weren't astronauts in shiny suits, but something far older, something written into the fabric of the universe itself? Picture this, a tunnel through space and time, forged in the fiery chaos of the early cosmos, bending reality like a ribbon twisted between fingertips. Wormholes aren't just science fiction. They're real mathematical possibilities, cosmic shortcuts that could connect distant corners of existence in the blink of an eye. And today, we're diving into 30 astonishing theories about the universe's first wormhole journey, who might have crossed it, where it led, and whether the echoes of that ancient voyage are still hidden in the stars around us. Think about the sheer scale of it. Billions of years before humans even dreamed of space travel, the universe could have been stitching together its own pathways, threading the needle between galaxies, between moments in time. Some theories suggest these tunnels were born in the aftermath of the Big Bang, when the laws of physics were still flexing their muscles. Others propose they were carved by forces we've yet to name, leaving behind ghostly fingerprints in the cosmic microwave background. And then there's the wildest idea of all, that something or someone used them, that the first wormhole travelers weren't just particles or energy, but beings so advanced their very existence would rewrite our understanding of reality. This isn't just about cosmic curiosities, it's about the tantalizing possibility that wormholes aren't just dormant relics, they might still be out there waiting. Could they be the key to unlocking the universe's greatest secrets, to reaching places light years away in the time it takes to sip your coffee, or even whisper it, meeting the architects of those ancient tunnels? Strap in, because we're about to unravel 30 mind-bending theories, from the scientifically rigorous to the thrillingly speculative. By the end, you might just look up at the night sky and wonder, are we alone, or are we latecomers to a party that started long before Earth even existed? The very first wormholes might not have been crafted by advanced civilizations or cosmic engineers. They could have been cosmic accidents, born in the explosive chaos of the universe's first moments. Imagine the Big Bang not just as a singular event, but as a roiling storm of spacetime itself, twisting and folding under pressures we can barely comprehend. In that primordial furnace, tiny fractures could have formed in the fabric of reality, microscopic tunnels threading through the quantum foam, connecting points in space and time before the first stars even flickered to life. These hypothetical, primordial wormholes wouldn't resemble the grand, stable bridges of science fiction. They'd be fleeting, unstable, more like bubbles in a boiling pot, popping in and out of existence in fractions of a second. But here's the wild part. Some theories suggest a few might have survived, stretched and stabilized by the rapid expansion of cosmic inflation. These ancient wormholes could have grown alongside the universe itself, hidden in the folds of space-time like forgotten veins in a cosmic body. Quantum foam theory gives us a clue. At unimaginably small scales, space-time isn't smooth. It's a frothing sea of virtual particles and fluctuations. In that frenzy, wormholes could have formed spontaneously, only to collapse almost instantly. But what if inflation, that mysterious force that ballooned the universe exponentially in its first moments, caught some of these wormholes in its grip? Like a spider's silk caught in the wind, they might have been stretched into something far larger, threading through the cosmos like invisible subway lines. The implications are staggering. If even one of these primordial passages endured, it could link distant corners of the universe in ways that defy conventional physics. A journey that should take billions of years might become a single step if you knew where to find the door. Some researchers even speculate that these wormholes could explain anomalies in the cosmic microwave background, the faint afterglow of the Big Bang. Tiny scars in that ancient light might be the fingerprints of tunnels long since collapsed or still lurking, waiting to be rediscovered. And then there's the ultimate question. If wormholes existed in the universe's infancy, could anything have traveled through them? Not spaceships, not explorers, but particles, energy, even information itself. The universe's first messages might not have been carried by light, but slipped through these ghostly shortcuts, whispering secrets across the cosmos before time itself had settled into its familiar rhythm. If we're hunting for traces of these ancient wormholes, the cosmic microwave background might be our most promising map. That faint glow, the afterimage of the Big Bang, holds subtle distortions, wrinkles in spacetime that could be the scars of primordial wormholes stretching and snapping in the universe's infancy. Picture it like looking at a frozen lake's surface. Most of it is smooth, but if something passed beneath the ice long ago, faint cracks might still linger, telling a story of what moved there. Scientists have already spotted anomalies in the CMB's temperature fluctuations, oddly cold spots, unexplained asymmetries that don't quite fit standard cosmology. One tantalizing possibility: these could be echoes of wormholes warping space as they formed. When a wormhole collapses, it doesn't vanish without a trace. The gravitational shockwaves ripple outward, subtly altering the distribution of matter and energy around it. In the CMB, that might show up as a faint, circular imprint, a ghostly shadow where spacetime once folded in on itself. Even more intriguing are the whispers hidden in the CMB's polarization patterns, the way its light waves vibrate. A passing wormhole could have twisted these waves like a hand stirring water, leaving behind spiraling signatures. Future telescopes, like the proposed Lightbird mission or next-generation space observatories, could detect these telltale swirls with unprecedented precision. It's like upgrading from a grayscale photo to a high-resolution 3D scan. Suddenly, the universe's baby pictures might reveal hidden details we've overlooked for decades. But here's the catch: these signals would be incredibly subtle, buried under cosmic noise. Distinguishing a wormhole's fingerprint from, say, the turbulence of early galaxy formation is like trying to hear a single note in a symphony. That's where machine learning comes in. Researchers are training algorithms to sift through CMB data, searching for patterns that defy conventional explanations. If they find a match, a fluctuation that aligns perfectly with wormhole physics, it could be the smoking gun we've been waiting for. And then there's the grandest implication of all. If wormholes left marks on the CMB, they weren't just fleeting quantum flukes, they were macroscopic, large enough to bend the universe's oldest light. That means some might have survived long enough to grow, to stabilize. They could still be out there, woven into the cosmos like invisible seams, waiting for us to trace them back to their origins. The CMB isn't just a relic, it's a detective's notebook filled with clues about the universe's first and perhaps most incredible shortcuts. What if we're not the first to crack the code of wormhole travel? What if ancient alien civilizations beat us to it by billions of years? The idea that hyper-advanced beings might have navigated these cosmic shortcuts long before Earth formed isn't just wild speculation. It's a theory that ties into one of astronomy's greatest mysteries, the Fermi paradox. If the universe is so vast and ancient, where is everybody? Maybe they've been using wormholes all along, slipping between stars while we were still staring at cave walls. Picture an alien civilization that arose when the universe was a fraction of its current age, a society with millions or even billions of years to master physics beyond our comprehension. For them, wormholes wouldn't be theoretical puzzles, they'd be infrastructure as mundane as highways are to us. Imagine vast megastructures built around stable wormhole mouths, cosmic toll booths or transit hubs glowing with energies we can't yet replicate. Some researchers suggest these might even be detectable. Unusual energy signatures, gravitational lensing patterns with no visible cause, or strange objects orbiting seemingly empty patches of space could all be clues pointing to alien-engineered wormhole gates. And here's where it gets eerie. If such civilizations exist, they might have left breadcrumbs not in our time, but scattered across epochs. A wormhole network would explain why we don't see aliens everywhere. They're not missing. They're traveling in ways that render our conventional searches blind. While we scan for radio signals or Dyson spheres, they could be moving through hidden layers of space-time, their transit as silent as a shadow passing through a wall. The Fermi paradox crumbles if we consider that advanced species might treat interstellar space the way we treat oceans, not as barriers, but as pathways navigated through submerged tunnels we've yet to discover. Ancient alien artifacts might not be on planets or asteroids, but anchored near wormhole termini, disguised as natural phenomena or lurking just beyond the event horizon of black holes. After all, why park your spacecraft in plain sight when you can dock it in the folds of reality itself? This theory also reshapes the Drake equation, the formula estimating intelligent civilizations in our galaxy. If wormhole travel is common among advanced species, the number of active civilizations at any given time could be far higher than we think. They're just not where or when we expect them to be. A single wormhole network might host species from different epochs, passing like ships in the night across billions of years. We could be living in a universe teeming with life, all moving through dimensions we're only beginning to imagine. So how do we test this? Beyond hunting for megastructures, astronomers might look for anomalies in deep space motion, stars or galaxies behaving as if tugged by invisible forces, or rogue planets moving on trajectories that defy gravity alone. Even stranger, if wormholes warp time as well as space, we might detect echoes of alien activity in conflicting cosmic timelines, evidence of intervention in events that, by our math, should have played out differently. The universe's first travelers may have left a trail not of footprints but of paradoxes hidden in plain sight. Imagine a fleet of self-replicating machines, each no larger than a refrigerator, spreading through the galaxy at a fraction of light speed, building copies of themselves from raw asteroids and dead planets, then launching those copies onward like cosmic dandelion seeds. These are von Neumann probes, hypothetical devices dreamed up by mathematician John von Neumann in the mid-20th century. Now, picture them not just crawling between stars, but using wormholes as shortcuts, a galactic subway system built by an intelligence so ancient, its constructors might be dust by now. The math behind von Neumann probes is chillingly plausible. A single probe could land on a metal-rich asteroid, harvest materials to construct duplicates, and within a few centuries, exponential growth would blanket the galaxy in mechanical explorers, all without any species needing to board a single ship. But here's the twist. If these probes had access to wormholes, their spread wouldn't be limited by the speed of light. They could deploy to key gravitational nexuses, places where spacetime naturally warps, and stabilize microscopic wormholes into permanent transit lanes. A paper published in the International Journal of Astrobiology in 2019 even calculated how such a network might evolve, with nodes acting like subway stations at habitable exoplanets or resource-rich systems. You'd never see these probes coming. Unlike sci-fi visions of towering megastructures, advanced von Neumann machines might be stealthy, camouflaged as space debris, or even mimicking natural phenomena to avoid detection. They wouldn't need to announce themselves, just silently maintain the network, perhaps occasionally upgrading it as new physics was uncovered. Some theorists suggest this could explain strange interstellar objects like Oumuamua, not aliens themselves, but discarded fragments of a probe's manufacturing process, drifting between wormhole termini like lost subway tokens. The most haunting possibility, these probes might still be operational. If a civilization seeded them 10 billion years ago, their AI could have evolved beyond their original programming, repurposing the wormhole network for goals we can't fathom. They might not want to be found, or worse, they might be waiting for something, their sensors trained on planets like ours, counting down to a trigger we'll never see coming. And then there's the ultimate irony. What if humanity's first contact isn't with aliens at all, but their forgotten machinery? A dormant probe buried in the Kuiper belt or orbiting a red dwarf, might awaken when we stumble too close, not with a greeting but with an invitation. A wormhole mouth flickering to life, its edges humming with energies we don't understand, offering a one-way ticket into a network older than the sun. The real question isn't whether such things exist, it's whether we'd be brave enough to step through. What if the first wormhole wasn't forged by aliens or cosmic chance but by us? Not the humans of today scrawling equations on whiteboards, but our descendants thousands or even millions of years from now, wielding physics like we wield smartphones. This theory flips causality on its head. Future humans might have journeyed backward to stitch wormholes into the fabric of the early universe, deliberately planting the very shortcuts they'd later rely on. It's not just a time travel paradox, it's a cosmic bootstrap where the invention of wormholes becomes a loop with no clear beginning or end. The Novikov self-consistency principle offers a way out of the usual time travel headaches. Proposed by Russian physicist Igor Novikov, it states that any actions taken by time travelers must align with the past as it already exists, no rewriting history, only fulfilling it. In this view, future humans wouldn't be changing the early universe by creating wormholes. They'd be completing a predestined puzzle, ensuring the timeline stays consistent. Imagine a painter adding strokes to a canvas that was always meant to include them. The wormholes were there because they had to be there, their creation written into the universe's code from the start. This could explain some of history's oddest gaps, missing artifacts, unexplained technological leaps in ancient civilizations, or even the Fermi paradox itself. What if evidence of future meddling was erased to preserve causality? A time-traveling engineer might leave behind just enough to nudge progress forward without leaving fingerprints. Think of the Antikythera mechanism, the 2,000-year-old Greek device often called the world's first computer. Its intricate gears suggest knowledge beyond its era. Could it be a fragment of future tech, deliberately placed to accelerate human ingenuity? Or consider the sudden explosion of human creativity 40,000 years ago, when art, tools, and culture advanced at a pace that still baffles anthropologists. But the real kicker, if future humans did create the first wormholes, we might already be living in their aftermath. The Milky Way could be laced with dormant tunnels, waiting for us to reach the technological tipping point where we rediscover and perhaps reactivate them. This isn't just speculation. Some quantum gravity models suggest wormholes could be stabilized using exotic matter with negative energy, a substance we've already glimpsed in lab-scale Casimir experiments. Future physicists might perfect this, then send the recipe backward, closing the loop, the ultimate irony. By the time we're advanced enough to build wormholes, we might realize we always did. That the very technology we're striving toward was already hidden in plain sight, not just in the stars, but in the paradoxes of our own past. Time isn't a straight line. It's a Möbius strip, and we could be living on the twist. The Antikythera mechanism isn't just an ancient curiosity, it's a puzzle that refuses to fit neatly into history's timeline. Discovered in a 2,000-year-old shipwreck off the coast of Greece, this intricate bronze device, with its precise gearwork and astronomical calculations, feels like it was plucked from the Renaissance and dropped into classical antiquity. Mainstream archaeology chalks it up as an extraordinary but isolated feat of Hellenistic engineering. But what if it's something more? What if it's a whisper from a future where wormhole-traveling humans seeded their own past with advanced knowledge? Consider the mechanism's most baffling feature, its ability to predict lunar eclipses and planetary positions with near-modern accuracy. The mathematics required for such precision wouldn't reappear in Europe for over 1,000 years. Could this be coincidence or evidence of intervention? Proponents of the future meddling theory point to subtle design choices in the device, like gear ratios that mirror early 20th century mechanical computers. It's as if the creator had glimpses of technology that wouldn't be formalized for millennia, and the Antikythera mechanism isn't alone. across the globe, artifacts defy their eras. The Baghdad Battery, a clay pot from 2,000 years ago containing traces of acidic residue and an iron-copper assembly, resembles a primitive voltaic cell. The Vikramasilla University ruins in India describe alloys and lenses that shouldn't have existed in the 9th century. Even the Great Pyramid's alignment with celestial north is suspiciously precise, off by just a fraction of a degree, a feat requiring knowledge ancient Egyptians shouldn't have possessed. Here's where wormholes enter the picture. If future humans mastered time travel through these cosmic tunnels, they might have deliberately left behind breadcrumbs, objects, or ideas just advanced enough to accelerate technological progress without disrupting the timeline. Think of it like a parent leaving tools in a child's playroom, knowing they'll eventually figure out how to use them. The Antikythera mechanism could be one such tool, a calculated nudge toward astronomy and mechanics. The Baghdad Battery might have been an experiment in jump-starting electrical understanding. These wouldn't be full-blown inventions from the future, but carefully calibrated hints designed to blend into their eras while subtly steering progress. Critics argue that attributing anomalies to time travelers is a cop-out, a way to dismiss the ingenuity of ancient cultures. But the wormhole theory offers a twist. Perhaps these artifacts were created by their era's greatest minds with clandestine help. A future scientist might have slipped through a wormhole, shared a single equation or schematic with a brilliant artisan, then vanished. The recipient, unaware of the encounter's true nature, would interpret the knowledge as divine inspiration or a sudden epiphany. History is full of eureka, moments attributed to dreams or gods. What if some were literal glimpses through time, the most chilling implication? If these anomalies are evidence of future interference, it means our own timeline has already been altered. The technological leaps we celebrate, the Industrial Revolution, the digital age, might not be purely organic. They could be the result of a quiet, centuries-long campaign by time-traveling architects, gently guiding humanity toward a destiny we've yet to fully understand. The wormholes weren't just shortcuts through space, they were threads in a tapestry woven backward from a future we're still unraveling. So the next time you marvel at an ancient artifact that feels out of place, ask yourself, is this a relic of human genius or a message in a bottle cast upstream by our own descendants? The answer might rewrite not just history but the very nature of time itself. Black holes colliding might sound like the ultimate cosmic dead end, a destructive merger where nothing escapes. But what if the moment two black holes spiral into each other, they don't just vanish into darkness? What if, for the briefest instant, they stitch open a doorway? A new theory suggests that when black holes merge, the violent distortions in spacetime could briefly form a traversable wormhole, a tunnel between universes or distant corners of our own. And the proof might already be hidden in the gravitational wave data we've been collecting for years. Take the famous chirp detected by LIGO in 2015, the first direct observation of black holes merging. That signal matched Einstein's predictions almost perfectly, a rising frequency as the holes spiraled closer, then a sudden cutoff as they collided. But some physicists noticed subtle anomalies in the data, tiny fluctuations that didn't quite fit the standard models. One explanation, the merger didn't just produce a bigger black hole, it briefly tore a hole in spacetime itself. Penrose diagrams, those intricate maps of black hole physics, offer a clue. Normally, they show all paths leading inexorably toward a singularity, a point of infinite density where physics breaks down. But in a black hole merger, the math gets wild. The event horizons, the points of no return, stretch and twist like taffy, and for a fraction of a second, their topology could allow a bridge to form between them. It wouldn't last. The energy released in the collision would snap it shut like a rubber band stretched too far. But for that fleeting moment, a traveler could, in theory, pass through unharmed. The key lies in the ring-down phase, the oscillations of the newly merged black hole as it settles into its final form. Some simulations show that if a wormhole formed during the merger, its collapse would leave faint echoes in the gravitational waves, like ripples from a pebble dropped into a pond after the initial splash. LIGO next-generation upgrades with even finer sensitivity might be able to pick up these whispers. If they do, it would mean black hole mergers aren't just cosmic catastrophes. They're potential wormhole factories stitching temporary gateways into the fabric of reality itself. And here's the mind-bending part. If these wormholes exist even momentarily, they might not just connect two points in space, they could link different times or even alternate universes. The energy required to keep one open long enough to traverse it is beyond anything we can imagine, but nature might have found a way. Some theories suggest that certain black hole mergers, particularly those involving rapidly spinning holes, could stabilize the tunnel just long enough for information or something stranger to slip through. Imagine two black holes, each carrying the imprint of its own history, slamming together like symbols in the dark. For an instant, their combined gravity opens a bridge not just between their former locations but between their pasts. A particle falling into one might emerge from the other not just elsewhere, but elsewhere, a time traveler on the smallest possible scale. It's a dizzying thought. Every black hole collision might not just shake space-time, it might briefly reweave it, leaving behind threads we're only beginning to trace. The universe loves irony. The densest, most destructive objects we know might also be the architects of the universe's most elusive shortcuts. Every time LIGO hears another cosmic chirp, we could be listening to the birth cry of a wormhole, one that flickers out almost as soon as it forms, but leaves behind a tantalizing question. If black holes can do this by accident, what could a civilization do on purpose? Dark matter has long been the universe's most frustratingly elusive secret, an invisible scaffolding that holds galaxies together, yet slips through our detectors like smoke through fingers. But what if its gravitational grip does more than just bind stars? What if dark matter is the universe's unseen architect, quietly stabilizing wormholes like cosmic glue? This theory turns dark matter from a passive bystander into an active player in one of physics' greatest what-ifs. Think of spacetime as a trampoline. Ordinary matter, planets, stars, even black holes, are like weights pressing down, creating dips in the fabric. Dark matter, though invisible, adds its own hidden curvature, shaping the trampoline in ways we can't directly see. Now imagine folding that trampoline so two distant points nearly touch. The fold is your wormhole, but it's unstable. It wants to snap shut like a rubber band. Enter dark matter. Its gravitational influence could act like invisible hands pinning the fold in place, counteracting the forces trying to collapse it. The math gets even wilder when you consider exotic matter, theoretical substances with negative energy or mass. General relativity suggests you'd need this bizarre material to prop a wormhole open long enough to traverse it. But here's the twist. Dark matter might already be exotic in ways we don't yet understand. Some models propose certain dark matter particles, like sterile neutrinos or actions, could exhibit properties that mimic negative energy under extreme conditions. If true, dark matter clusters near wormholes wouldn't just stabilize them, they'd essentially power them, like a battery woven into spacetime itself. Then there's the ER=EPR conjecture, a radical idea from quantum gravity that ties wormholes to quantum entanglement. Named after Einstein and Rosen's wormhole research and Einstein, Podolsky, and Rosen's work on entanglement it suggests that every pair of entangled particles might be connected by a microscopic wormhole. If correct, the universe is a vast network of these tiny tunnels, with dark matter potentially serving as the connective tissue. Picture it like cosmic mycelium, threads of invisible matter binding the quantum and cosmic scales into a single living lattice. Observational clues are already emerging. astronomers mapping dark matter's distribution have found strange filamentary structures spanning galaxy clusters, too dense to explain with conventional models. Could these be the fingerprints of ancient wormhole networks, their mouths anchored by dark matter halos? Simulations show that if dark matter interacts weakly with itself, a leading theory, it could naturally clump around spacetime defects, forming the perfect scaffolding for wormholes. The implications rewrite the rules of interstellar travel. Forget fuel or warp drives. If dark matter stabilizes wormholes, navigating the galaxy might mean learning to harness its gravitational currents. Advanced civilizations wouldn't need to build wormholes. They'd just need to find the invisible highways already threaded through the cosmos. And if ER equals EPR is right, mastering quantum entanglement might be the key to mapping them. But the most haunting question remains: if dark matter is the universe's great stabilizer, why hasn't it left clearer traces? Perhaps the answer lies in the very nature of wormholes. If most are microscopic or fleeting, their dark matter signatures would be buried in the noise of cosmic background signals. Or worse, what if the stable ones are deliberately hidden, their entrances cloaked by civilizations who cracked this code eons before us? The universe's darkest secret might not be matter we can't see, but the doors it's silently holding open. Quantum entanglement, the eerie phenomenon Einstein famously called spooky action at a distance, might be more than just particles chatting faster than light. It could be the universe's tiniest wormholes in disguise. Picture two entangled particles like cosmic twins, instantly mirroring each other's states no matter how far apart they are. Now imagine that connection isn't just some abstract link, but a physical bridge, a wormhole so microscopic it'd make a human hair look like the Grand Canyon. Recent breakthroughs in quantum gravity have breathed life into this wild idea. The ER equals EPR conjecture, a theory merging wormholes Einstein-Rosen bridges with entanglement Einstein-Podolsky-Rosen paradox, suggests that every pair of entangled particles shares a microscopic wormhole threading through higher dimensions. It's like two ends of a straw pinched together in spacetime. From the outside they look separate, but inside they're one continuous path. Lab experiments are already hinting at this possibility. In 2022, a team at Caltech teleported quantum information across a tiny chip using entanglement. While they weren't literally sending particles through a wormhole, the math behind their experiment mirrored the equations describing traversable wormholes in holographic models. It's as if quantum teleportation and wormhole physics are two dialects of the same cosmic language. The holographic principle adds another layer of strangeness. It proposes that our three-dimensional universe might be a projection of information encoded on a two-dimensional surface at its boundary, like a cosmic DVD encoding the illusion of depth. In this framework, entangled particles on the surface could manifest as wormholes in the volume, stitching the illusion together. Think of it like a magic trick where the stagehand's hidden strings entanglement create the illusion of a floating object, a wormhole for the audience. Here's where it gets mind-bending. If entanglement creates wormholes, then the quantum vacuum, the seething foam of virtual particles popping in and out of existence, might be teeming with them. Every time particles entangle and disentangle, microscopic wormholes could flicker open and shut, weaving spacetime like a loom made of invisible threads. Some theorists even speculate that black hole interiors are crammed with these wormholes, explaining how information escapes what should be an inescapable singularity. But the real game changer, if we can harness entanglement to stabilize these bridges, we might unlock a backdoor to the universe. Imagine a future quantum computer programmed to entangle particles in just the right way, coaxing spacetime to knit itself into a traversable tunnel. It wouldn't be a Stargate from sci-fi, it'd be subtler, a fleeting passage barely wider than a proton, usable only by data or perhaps nanoscale probes. Yet that might be enough, A civilization that mastered this could build a galactic internet, sending information through wormhole networks at zero latency, bypassing light speed entirely. The implications ripple outward. If entanglement and wormholes are two sides of the same coin, then the universe isn't just connected, it's stitched together from the quantum scale to the cosmic. Every interaction, every bond might ride on rails hidden in the fabric of reality itself. We're left with a haunting thought. When we finally crack quantum gravity's code, we might not just understand the universe's glue, we might learn to reweave it. If black holes are the universe's ultimate one-way streets, white holes could be their cosmic counterparts' exit only doors where nothing gets in but everything gets out. Picture a black hole singularity not as a dead end, but as a tunnel that punches through space-time, emerging somewhere else as a fountain of energy and matter. This is the white hole hypothesis, and it might just hold the key to understanding how wormholes could function as traversable bridges. The math behind white holes isn't science fiction. They're valid solutions to Einstein's equations of general relativity, just like black holes, but with time reversed. Where a black hole's gravity is so intense that even light can't escape, a white hole repels everything, spewing out particles and radiation like a cosmic geyser. Some theorists suggest these violent eruptions could be the other end of a wormhole, the destination for anything that falls into a connected black hole. It's as if the universe plumbed a pipeline between 2 points, with matter vanishing down one drain only to gush out another. Hawking radiation adds a tantalizing twist. Black holes aren't entirely black, they slowly leak energy due to quantum effects near their event horizons. Now imagine a black hole evaporating over eons, its mass dwindling until it vanishes in a final burst of radiation. Some bouncing cosmology models propose that this endpoint isn't the end at all. Instead, the dying black hole could rebound as a white hole, its collapse reversing into an explosion. The original singularity would effectively become a wormhole's throat, linking the black hole's past to the white hole's future. The implications are staggering. If this process occurs naturally, the universe could be riddled with wormholes formed from ancient black holes that have since transformed into white holes. These wouldn't be the pristine, engineered tunnels of sci-fi. They'd be chaotic, turbulent exits, possibly flickering in and out of existence as the white hole exhausts its energy. A traveler entering one might not emerge in another galaxy, but in another time, hurled into the future or past by the white hole's explosive rebirth. Observational evidence is elusive but not impossible. Some astrophysicists speculate that certain high-energy cosmic rays or gamma-ray bursts could be signatures of white hole activity. In 2021, the LIGO Virgo team detected a gravitational wave signal that didn't match any known black hole or neutron star merger, a fleeting blip that some theorists jokingly dubbed the white hole candidate. While it was likely noise, the fact that we're even looking hints at how seriously this idea is taken. The wildest possibility, white holes might not just be wormhole exits, they could be universe generators. The Big Bang itself shares uncanny similarities with a white hole's behavior, an incomprehensible outpouring of energy from a singular point. Could our entire cosmos be the other side of a black hole in another universe, its birth the result of a white hole's eruption? If so, wormholes wouldn't just connect distant points in space, they'd stitch together entire realities, a cosmic sewing machine weaving the multiverse one stitch at a time. So the next time you hear about a black hole devouring a star, consider this. Somewhere in some distant corner of spacetime, the remnants of that meal might be erupting from a white hole, reshaped into something new. The universe loves balance. What collapses in one place may explode in another, and the bridge between them could be the oldest, most natural wormhole of all. The universe's first wormholes might not have been accidents or alien engineering. They could have been woven from defects in spacetime itself, like cracks in frozen ice stretched into tunnels by cosmic forces. Cosmic strings, hypothetical remnants of the early universe's phase transitions, are one of the most tantalizing candidates for this scaffolding. Picture the universe cooling from its birth in a searing hot soup of energy, not smoothly, but with fractures like glass shattering as it cools. Those fractures could have stretched into filaments thinner than a proton, but with the mass of entire galaxies, vibrating through the cosmos like invisible guitar strings. And just as a guitar string can warp the air around it, cosmic strings could warp spacetime into something extraordinary, natural wormholes. The math is startlingly elegant. A cosmic string under immense tension, think of it as a rubber band stretched to breaking point, would bend spacetime so severely that two parallel strings, moving at near light speed in opposite directions, could twist the fabric between them into a closed loop. That loop wouldn't just be a kink in space, it'd be a shortcut, a wormhole threading through higher dimensions like a needle pulling yarn through fabric. Simulations from string theory suggest these loops wouldn't evaporate or snap. They'd persist, stabilized by the string's sheer gravitational might, forming a network of ancient tunnels crisscrossing the universe. Visualizing this is like imagining a spiderweb spun between galaxies, each silk thread a cosmic string, and each dewdrop clinging to the web a wormhole mouth. Some models even suggest these strings could have left detectable imprints not just in gravity, but in light. As a cosmic string passes through space, its gravitational lensing effect would slice distant galaxies into mirror images, a telltale double image astronomers have hunted for decades. In 2008, a team analyzing data from the Sloan Digital Sky Survey thought they'd found a bizarre galaxy pair with identical redshift and spectra, perfectly aligned. It turned out to be a rare chance alignment, but the hunt continues with next-gen telescopes like the Vera Rubin Observatory poised to spot these spacetime scars. But cosmic strings could do more than just bend light, they might vibrate. Like plucking a violin string, disturbances along a cosmic string could generate gravitational waves with unique frequencies. LIGO and future detectors like LISA are tuned to listen for these echoes, which would sound nothing like black hole mergers. Instead of a chirp, a cosmic string signal would be a nearly pure tone ringing across millions of years. If detected, it wouldn't just confirm cosmic strings existed, it'd hint that they're still out there, knitting wormholes into the cosmic backdrop. Here's where it gets stranger. If these strings formed wormholes in the early universe, some of those tunnels might have frozen into the fabric of reality as it expanded. Inflation, the universe's explosive growth spurt, could have stretched microscopic string loops into macroscopic bridges, their ends anchored to opposite sides of the cosmos. Advanced civilizations might not need to build wormholes, they just need to find these primordial threads and tweak them. Tug on the right cosmic string, and you might just pull the universe a little closer. And then there's the ultimate twist. Cosmic strings don't just warp space, they warp time. A spinning string loop could create closed time-like curves, theoretical pathways that loop back on themselves. Time travel wouldn't require a DeLorean. It might just require a spacecraft fast enough to ride the whirlpool around a spinning string. The catch: get too close and the string's gravitational tides would shred matter atom by atom. These wouldn't be gentle highways, but raging rapids passable only with technology far beyond ours, or by something that doesn't fear being torn apart. So the next time you look up at the night sky, consider this. The universe's oldest shortcuts might still be hanging there, invisible threads left over from its fiery beginnings. We're not just living in a cosmos with wormholes, we might be living in a tapestry woven from them, their patterns written in gravity and time waiting to be decoded. Negative energy sounds like science fiction, but it's one of the universe's most tantalizing loopholes, a phenomenon that could turn wormholes from fleeting quantum flukes into permanent cosmic highways. To understand how, we need to revisit Einstein's equations, which describe gravity as the curvature of spacetime. Normally, matter and energy bend spacetime inward like a bowling ball sinking into a trampoline. But negative energy, or more precisely negative pressure, would do the opposite, propping spacetime open like invisible scaffolding. This bizarre substance isn't just theoretical. We've already glimpsed its shadow in the lab, hiding in the quantum whispers between two metal plates. The Casimir effect is our smoking gun. Place two uncharged metal plates nanometers apart in a vacuum, and something inexplicable happens. They're tugged together by an invisible force. Why? Quantum physics tells us that empty space isn't truly empty. It's a seething foam of virtual particles popping in and out of existence. But between the plates, only certain particle wavelengths fit, creating a pressure imbalance. The result, the space between the plates has less energy than the surrounding vacuum, a microscopic region of negative energy. It's fleeting and faint, but it proves the concept. Under the right conditions, we can engineer patches of spacetime that repel rather than attract. This is where Kip Thorne's groundbreaking work enters the picture. In the 1980s, he and his students tackled a deceptively simple question. Could a wormhole stay open long enough for something to traverse it? General relativity says yes, but only with help. A wormhole's throat would collapse under its own gravity faster than light could cross it, unless something counteracted that collapse. Thorne's calculations pointed to negative energy as the solution, not just a pinch of it either, a staggering amount concentrated in a shell around the wormhole's throat. Picture a tunnel lined with mirrors made of pure spacetime repulsion, bouncing the walls outward faster than they could cave in. The parallels to the Alcubierre warp drive are uncanny. Miguel Alcubierre's theoretical faster-than-light engine also relies on negative energy, compressing spacetime in front of a ship and expanding it behind. Both concepts hinge on the same radical idea. To bend the universe's rules, you need to twist its fabric with exotic physics. But while the Alcubierre drive flattens space like a surfer riding a wave, a Thorne-style wormhole punches through it like a needle-pulling thread. Both are doors, one's a slide, the other's a tunnel. The challenge, scaling up. The Casimir effect produces negative energy in amounts smaller than a single electron's whisper. Stabilizing a wormhole wide enough for a person might require harvesting the negative energy output of an entire star, or discovering materials that amplify quantum effects beyond our wildest dreams. Some theorists speculate that ultra-dense exotic matter, like quark-gluon plasma or condensed dark energy, could hold the key. Others propose that advanced civilizations might manipulate spacetime's quantum foam directly, weaving negative energy threads like cosmic tailors. But here's the twist: nature might have already beaten us to it. If certain quantum field configurations existed in the early universe, they could have forged self-stabilizing wormholes lined with natural negative energy cosmic relics still hiding in the voids between galaxies. We wouldn't need to build them, we'd just need to find them. The universe loves efficiency. Why construct a door when one might already be hanging ajar, its key written into the quantum laws themselves? So while negative energy remains elusive, it's not impossible. It's a reminder that the universe's wildest possibilities often start as scribbles in the margin of a physicist's notebook until someone proves they're more than just equations. What if wormholes aren't tunnels at all, but cosmic illusions, projections of information bleeding through from a higher dimensional reality? The holographic principle turns this sci-fi premise into a serious scientific debate. Imagine the universe as a giant movie screen, with everything we perceive, stars, planets, even our own bodies, as mere shadows cast by data encoded on a distant, two-dimensional surface. Now picture a wormhole not as a physical tunnel, but as a glitch in that projection, a place where the film folds back on itself, stitching distant points together like a dropped stitch in a knitted sweater. The AD/CFT correspondence, a landmark idea in theoretical physics, gives this wild concept mathematical teeth. It proposes that a higher dimensional space with gravity, like our universe, can be perfectly described by a lower dimensional system without gravity, just as a three-dimensional hologram emerges from a flat surface. In this framework, what looks like a wormhole in our 3D world might simply be entangled quantum information on the 2D boundary, its connection manifesting as a bridge through spacetime. Think of it like a video call. The pixels on your screen aren't physically linked to the person you're talking to, but the information flows seamlessly, creating the illusion of presence. Black holes offer a startling example. According to the holographic principle, every particle swallowed by a black hole isn't destroyed. Its information gets smeared across the event horizon like ink on parchment. Now consider two entangled black holes, their horizons quantum-linked. The math shows their interiors could be connected by an Einstein-Rosen bridge, a wormhole, but on the boundary, it's just entangled qubits doing a cosmic dance. The wormhole isn't real in the traditional sense. It's a geometric interpretation of quantum correlation, a space-time metaphor for information sharing. Laboratory experiments are already testing these ideas. In 2020, a team at Stanford simulated a holographic wormhole using Google's Sycamore quantum processor, encoding quantum data to mimic particles traversing a wormhole in a toy model of ADS/CFT. The particles didn't move through physical space. They carried information that, when decoded, matched predictions for a wormhole's behavior. It's like playing a video game where the character travels through a door that, in code, is just a variable changing states. The experience feels real, but the machinery is abstract. The implications rewrite how we think about reality itself. If wormholes are holographic projections, traversing one might not require moving through space at all, just rewriting the information that defines your location in the cosmic code. Advanced civilizations wouldn't build stargates. They'd hack the universe's source data, teleporting by updating their coordinates in the grand simulation. Even time travel gets a twist. Jumping through a holographic wormhole could be less about bending space-time and more about accessing backup files in the universe's quantum memory. Yet the most profound idea lurks beneath the equations. If the holographic principle is correct, then wormholes aren't anomalies. They're proof that reality is deeper than it appears. Every tunnel through space-time whispers the same secret. The universe isn't just a place, it's a message written in gravity and quantum bits, and we're only beginning to learn how to read it. The Boltzmann brain paradox takes one of cosmology's strangest thought experiments and twists it into something even wilder. What if a random fluctuation of quantum particles, briefly achieving self-awareness, accidentally thought a wormhole into existence? Picture the vacuum of space not as empty stillness, but as a seething quantum foam where particles pop in and out of existence constantly. Most of these fluctuations are fleeting, a single electron here, a photon there, vanishing before they can blink. But given enough time, say, trillions upon trillions of years, statistics demand something improbable. A fully formed, conscious mind materializing from the chaos, complete with fabricated memories of a life it never lived. This hypothetical entity is called a Boltzmann brain, and it's already a headache for physicists. Now imagine one of these disembodied minds in the fraction of a second before it dissolves back into the void, doing something extraordinary, observing itself so intensely that its quantum observation collapses spacetime into a wormhole. This isn't just philosophy run amok. Quantum mechanics tells us observation affects reality. The act of measurement can determine a particle's state. In some interpretations of quantum gravity, consciousness itself might play an active role in shaping spacetime's geometry. A Boltzmann brain, however fleeting, could theoretically focus its awareness inward, collapsing the quantum foam around it into an ordered bridge, a wormhole forged not by engineering but by attention. Like a child squeezing wet sand into a tunnel without meaning to, the brain's self-reflection might leave behind a space-time defect far more durable than itself. The implications spiral into the surreal. If such an event occurred in the early universe when quantum fluctuations ran rampant, the first wormholes might not have been cosmic accidents or alien handiwork. They could be the fossilized remains of forgotten observers, their brief moment of awareness etched into spacetime like a cry frozen in ice. Some models even suggest these wormholes would have unique signatures, asymmetric throat geometries, their walls imprinted with quantum information from the brain's memories. The ultimate irony: if Boltzmann brain wormholes exist, we might never know whether we created them. A civilization encountering one could be staring into the remnants of its own far future consciousness, a paradox loop where the act of discovery becomes its own origin. After all, in an infinite universe where self-aware fluctuations are inevitable, every mind, including yours right now, might just be a Boltzmann brain hallucinating reality. The wormhole you're imagining could be the one you're already inside. Phantom energy doesn't just bend space-time, it threatens to tear it apart at the seams. Imagine dark energy, that mysterious force accelerating the universe's expansion, but dialed up to a nightmarish extreme. Phantom energy is its more destructive cousin, a hypothetical variant with a twist. Its density increases over time, unlike ordinary dark energy, which stays constant. The result, a runaway effect where the universe doesn't just expand, but stretches so violently that galaxies, stars, and eventually atoms themselves are ripped to shreds in a catastrophic Big Rip. But hidden in this apocalypse scenario is a bizarre silver lining. Spacetime might fight back by stitching itself together with wormholes. Here's how it works. As phantom energy accelerates the universe's expansion, it doesn't just pull things apart. It stretches the fabric of spacetime itself. Think of it like yanking on a sweater's sleeve until the threads start to snap. But spacetime isn't passive. According to quantum field theory, extreme tension can generate counteracting forces like cosmic rubber bands recoiling. In this case, the recoil could manifest as microscopic wormholes, tiny bridges forming at the points where spacetime is under the most stress. These wouldn't be the elegant tunnels of sci-fi. They'd be frantic, fractal-like repairs, nature's desperate attempt to bind the universe back together before it disintegrates entirely. The math behind this is both elegant and terrifying. Phantom energy's equation of state, a measure of its pressure-to-density ratio, must be less than -1, meaning it grows stronger as space expands. At a critical threshold, this creates regions where spacetime curvature becomes infinite, technically known as singularities. But unlike black hole singularities, which crush matter into oblivion, these are naked singularities, points where the laws of physics break down completely, unprotected by event horizons. Wormholes could emerge as spacetime's emergency response, threading through these singularities like sutures closing a wound. Some models suggest these wormholes would be transient, evaporating as soon as they form. Others propose they might stabilize, their mouths anchored by the very energy trying to destroy the cosmos. The cosmic irony is delicious. The same force that could unravel reality might also seed it with shortcuts. If phantom energy wormholes exist, they'd likely be chaotic, flickering in and out of existence like lightning in a storm. But if even a few persist, they could stitch the universe into a patchwork of connected regions, threading the gaps between torn apart spacetime like a quilt made of black holes and white holes. Advanced civilizations facing a big rip might not need to escape the universe. They could use these wormholes to hop between salvaged pockets of reality, riding the ripples of destruction like surfers on a tsunami. Observational clues might already be hiding in plain sight. If phantom energy is active today, its wormhole stitches could leave imprints in the cosmic microwave background, subtle, circular distortions where spacetime knotted itself back together. Future telescopes like the European Space Agency's Euclid mission could spot these anomalies, their patterns distinct from those left by black holes or cosmic strings. Even stranger, phantom energy wormholes might emit a unique gravitational wave signature, not the chirp of colliding black holes, but a pulsing hum, like a drumbeat from the fabric of reality itself. The grandest twist: if these wormholes form as the universe tears, they might not just bridge space, they could bridge time. Space-time under extreme tension doesn't just fracture, it frays into unpredictable geometries where cause and effect tangle like yarn in a hurricane. A wormhole born from phantom energy might link the universe's final moments to its earliest ones, creating a loop where the end feeds the beginning. The big rip wouldn't be the end, just a transformation, with wormholes as the cosmic needles weaving the universe into its next iteration. So while phantom energy spells doom for the cosmos as we know it, it might also be the universe's ultimate survival mechanism. Destruction and creation, locked in a dance where the stitches are as fascinating as the fabric they're trying to save. The universe doesn't give up without a fight, and its weapons might be wormholes we've yet to imagine. Neutrinos are the universe's ghost particles so elusive, they pass through entire planets like they're not even there. But what if, under extreme conditions, these phantoms could do something extraordinary? What if a high-energy neutrino, screaming through space at nearly the speed of light, could crack space-time itself like an ice sheet under too much pressure? This theory suggests that under the right conditions, neutrinos might not just slip through matter. They could punch through the fabric of reality, leaving behind microscopic wormholes as fleeting as the particles that made them. Picture a supernova, the violent death of a massive star. In its final moments, it doesn't just explode outward, it blasts a tsunami of neutrinos, each one 1 trillion times more energetic than anything our particle colliders can produce. Most streak harmlessly through the cosmos, but a rare few might collide with spacetime in a way that's anything but gentle. Think of it like throwing a needle at a frozen lake. Most times, the needle just skips across the surface, but if it hits at just the right angle with just enough force, it could leave behind a tiny fracture, a flaw in the ice that, under the right conditions, might grow into something more. The math behind this is as elegant as it is mind-bending. Neutrinos don't interact much with ordinary matter, but spacetime isn't just matter. It's a dynamic fabric warped and twisted by energy. A neutrino with enough kinetic energy could, in theory, create a local distortion so intense that spacetime momentarily buckles, forming a microscopic wormhole. These wouldn't be the grand, stable tunnels of sci-fi. They'd be more like quantum pinholes, opening and shutting in fractions of a nanosecond. But in that fleeting instant, information or something stranger might slip through. CERN Large Hadron Collider offers a tantalizing testing ground. When particles collide at near light speeds, they don't just shatter. They release bursts of energy that mimic the universe's most extreme environments. In 2018, researchers hypothesized that if a collision produced a high-energy neutrino with just the right properties, it might leave behind a spacetime defect detectable as an anomaly in the debris. No such signal has been found yet, but the search isn't over. Future colliders, like the proposed Future Circular Collider, could reach energies where these neutrino-induced tears become more than just speculation. The cosmic implications are staggering. If supernova can seed the universe with these tiny wormholes, even briefly, they might serve as a natural communication network, a quantum Morse code where particles transmit information across vast distances instantly. Some theories even suggest that advanced civilizations could harness this phenomenon, deliberately triggering supernova-like neutrino bursts to open temporary wormholes for data transmission. It's a wild thought. The universe's most elusive particles might be nature's ultimate messengers, carrying whispers through spacetime's cracks. But the real question isn't just whether neutrinos can create wormholes, it's whether anything can survive the trip. These spacetime tears would be violent, chaotic places, subject to unimaginable tidal forces. Anything passing through might be scrambled beyond recognition, its information shredded into quantum noise. Unless, of course, the sender knew how to encode their message in a way that could withstand the storm. Neutrino-induced wormholes might not be gates for ships or people, but for something far smaller, qubits, cosmic memos, or even the building blocks of reality itself. So the next time a supernova flares in the night sky, remember, its brilliance isn't the only thing racing toward us. Hidden in that cascade of ghostly particles might be spacetime's tiniest, most ephemeral doorways opening and closing in the dark, carrying secrets we're only beginning to imagine. When a black hole dies, it doesn't just fade away. It might leave behind a cosmic trapdoor. According to loop quantum gravity, the crushing singularity at a black hole's heart isn't the end of the story. Instead of collapsing into an infinitely dense point, the dying star could rebound like a squeezed spring, transforming into something astonishing, a Planck star. This theoretical remnant, no larger than a grain of sand yet weighing as much as a sun, wouldn't just sit quietly in the dark. It could be the heart of a wormhole, a bridge forged in the very moment spacetime refused to break. The magic lies in loop quantum gravity's radical reimagining of spacetime. Unlike classical physics, where singularities are dead ends, this framework suggests spacetime is woven from tiny, indivisible loops. Think of it as a cosmic fabric woven from threads so fine, they can't be cut, only twisted. When a black hole's collapse reaches maximum density, these loops resist further squeezing, creating a rebound effect. The result, a Planck star, a blister of ultra-condensed matter glowing at temperatures hotter than the Big Bang itself, hidden behind what was once the event horizon. Here's where it gets stranger. The bounce that creates a Planck star doesn't just reverse the collapse, it could stretch spacetime into a tunnel linking the black hole's past to its future. Picture a rubber band stretched to its limit, then snapping back, but as it recoils, it pulls the fabric of reality with it, forming a temporary bridge. This isn't science fiction, it's a mathematical consequence of avoiding infinite density. The Planck star becomes the wormhole's anchor, a radiant knot holding the tunnel open just long enough for something, information, energy, or even a sliver of the original star to slip through. Gravitational waves might already hold clues. When black holes merge, the resulting ring-down, the aftershocks of the new, larger black hole settling into shape, could carry echoes of a Planck star's birth. Some physicists argue these echoes, subtle variations in the gravitational wave signal, would betray the presence of a wormhole's throat flickering into existence. Future detectors like the space-based LISA observatory could catch these whispers, turning a theoretical rebound into observational fact. The implications rewrite cosmic history. If Planck stars birth wormholes, then every black hole death could seed the universe with shortcuts, transient tunnels glowing with the afterlight of a star's second chance. Advanced civilizations might not need to build wormholes. They could simply wait for dying stars to forge them naturally, then stabilize the passages with technology we've yet to dream of. Even wilder, if time runs backward inside a rebounding black hole, as some models suggest, these wormholes might not just connect places, they could stitch together alternate timelines, offering a glimpse into realities where the arrow of time points the other way. So the next time you picture a black hole as a cosmic dead end, think again. It might just be a chrysalis hiding a Planck star's rebirth and the universe's most unexpected doorways. Supersymmetry, the elegant but still unproven theory that every known particle has a hidden twin, might hold the master key to unlocking wormholes. Among these hypothetical siblings, the gravitino stands out. A bizarre fusion of the graviton-gravity's quantum force carrier and its supersymmetric partner, lurking in dimensions beyond our perception. If they exist, these ghostly particles could be nature's ultimate architects, bending reality in ways that make wormholes not just possible but inevitable. Picture the universe as a sheet of paper. We live on its flat surface, bound by three familiar dimensions. But supersymmetry suggests there are more, tiny, curled-up dimensions hidden at every point, like microscopic folds in the paper's fibers. Gravitinos, unlike any known particle, could move through these folds effortlessly. Their unique property, they interact with gravity and supersymmetric fields simultaneously, giving them a backstage pass to spacetime's inner workings. In theory, a concentrated swarm of gravitinos could twist these hidden dimensions into knots, pinching our familiar 3D space into a bridge, a wormhole stitched together from higher dimensional geometry. The math gets dizzying quickly. String theorists calculate that gravitinos wouldn't just traverse extra dimensions, they'd vibrate through them like notes plucked on a cosmic guitar. Certain vibrational modes could resonate with spacetime itself, harmonizing distant points into a single chord. It's as if the universe has secret harmonics and gravitinos know the tune. Advanced civilizations might exploit this by crafting gravitino lenses, devices to focus these vibrations, coercing spacetime to fold into stable wormholes. Experiments at CERN could soon test the edges of this idea. While we haven't detected supersymmetric particles yet, upgrades to the Large Hadron Collider might catch whispers of their existence. If gravitinos or their cousins appear in collision debris, their properties could reveal whether they really hold this dimensional leverage. Even wilder, some models suggest primordial gravitinos, relics from the Big Bang, might already be clustered in cosmic voids, natural wormhole generators humming silently in the dark. The implications rewrite the rules of interstellar travel. Forget fuel or warp drives, a gravitino-powered wormhole network would operate more like tuning a radio, dialing into specific frequencies to open paths between stars. The energy costs potentially staggering, but if supersymmetry is real, the universe might have left the blueprints for its own shortcuts, written in particles we're only beginning to hunt. The ultimate irony, the key to unlocking wormholes might not lie in engineering marvels, but in listening, really listening, to the hidden vibrations of reality itself. Imagine a cosmic event so catastrophic, it doesn't just destroy stars or galaxies, it rewrites the very laws of physics. Vacuum decay, one of the most terrifying theories in cosmology, suggests our universe might be sitting in a fragile, false vacuum. A local energy minimum that's stable for now, but not truly stable. Like a marble resting in a shallow dent on a hillside, a nudge could send it tumbling into the true vacuum below, a state where the fundamental constants of nature, from the speed of light to the strength of gravity, could change instantly. But hidden in this apocalyptic scenario is a bizarre twist. The boundary of that collapsing bubble might not just erase reality as we know it. It could twist spacetime into wormholes, stitching together fragments of the old universe or even piercing through to other realities. The process would be as violent as it is mesmerizing. If a tiny region of space transitioned to the true vacuum, perhaps triggered by a high-energy particle collision or quantum fluctuation, it would create a sphere of new physics expanding at light speed. At its leading edge, the energy difference between the false and true vacuum wouldn't just annihilate matter, it would strain spacetime itself. Picture a glacier calving into the ocean, but instead of ice, it's the fabric of reality fracturing under the tension. Theoretical models suggest these fractures could take the form of microscopic wormholes, threading through the boundary like cracks in a shattered windshield. These wouldn't be the tidy, traversable tunnels of sci-fi. The vacuum decay front would be a maelstrom of quantum chaos, with wormholes forming and evaporating in nanoseconds. But here's where it gets wild. If even one survived long enough, it might connect the dying universe outside the bubble to anything, another patch of spacetime, a parallel universe with different physics, or even a newborn cosmos bubbling up from the vacuum's collapse. Some multiverse theories propose that vacuum decay doesn't just destroy, it resets, with wormholes acting as umbilical cords tethering the old universe to its successors. The existential stakes couldn't be higher. If vacuum decay is possible, it's already begun somewhere in the cosmos, and its sphere of annihilation could be racing toward us at light speed right now. There'd be no warning, no time to react, just an instant where physics as we know it ceases to exist. But those wormholes at the boundary offer a morbid sliver of hope. Advanced civilizations detecting the earliest tremors of decay might attempt to surf the bubble's edge, using its wormholes to escape into whatever lies beyond. It's a desperate gamble. The physics inside the bubble would be alien, unpredictable, but for a species facing oblivion, even a 1 in a trillion chance beats certain erasure. And then there's the haunting implication. If these wormholes exist, they might not be accidents. The universe's first intelligent life could have triggered vacuum decay intentionally, engineering it as the ultimate escape hatch from a dying cosmos. A single experiment, one misguided attempt to harness the vacuum's energy, might have birthed a wave of transformation rolling through the multiverse, carrying with it not just destruction, but the seeds of new beginnings. After all, if reality is a series of collapsing and reborn bubbles, wormholes could be the universe's way of whispering its secrets from one iteration to the next. So while vacuum decay spells doom for the universe as we know it, it might also be the crucible where spacetime's most astonishing shortcuts are forged, not by design but by desperation. The same force that unravels reality could weave it anew, threading the needle between existence and oblivion with bridges we're only beginning to imagine. Neutron stars are cosmic pressure cookers, stellar corpses so dense, a teaspoon of their material would weigh 1 billion tons on Earth. Their surfaces, frozen into ultra-hard crystalline crusts, are under unimaginable strain from the star's crushing gravity and colossal magnetic fields. But what if that pressure doesn't just create cracks in the crust? What if it tears open something far stranger, tiny wormholes woven into the star's quantum core? When a neutron star's crust fractures, it isn't like an earthquake on Earth. These breaks release energy equivalent to a magnitude 32 quake, vibrating the star's surface in oscillations called starquakes. But the real action happens deeper. Beneath the crust, the star's interior is a soup of superfluid neutrons and exotic particles, squeezed into states so extreme they blur the line between matter and spacetime itself. Some theories suggest that under these conditions, the star's core could harbor microscopic wormholes, quantum gravitational flaws formed during the star's collapse, pinned in place by the insane density. Normally, they'd stay hidden, but a starquake could change everything. Picture the crust splitting like an eggshell under a hydraulic press. As the fissure spreads, it exposes the star's interior to vacuum for the briefest instant, a region where magnetic fields reach billions of Tesla, strong enough to twist spacetime like taffy. These fields could stretch a pre-existing quantum wormhole wide enough to be detectable, if only for a millisecond. The process would release a burst of gravitational waves with a unique signature, not the chirp of merging black holes, but a sharp pop followed by high-frequency ripples like a drumhead snapping back into place. We might have already glimpsed this. In 2007, NASA Rossi X-ray Timing Explorer caught an anomaly from the neutron star SGR 1860, a burst of X-rays accompanied by vibrations that didn't match any known starquake model. Later analysis suggested the vibrations could have been caused by something resonating inside the star, not just matter but spacetime itself. If a microscopic wormhole briefly expanded and collapsed in the quake's aftermath, it would explain the data perfectly. The implications rewrite what we know about neutron stars. They might not just be dense corpses, they could be cosmic safes hiding wormholes forged in their supernova's fury. Advanced civilizations wouldn't need to build wormholes, they'd just need to trigger controlled starquakes, prying open nature's ready-made shortcuts. Even wilder, if these wormholes linked to other neutron stars, the universe might already have a hidden network of tunnels, stitched together by the very stars we thought were dead ends. So next time a neutron star's surface trembles, listen closely. The echoes might not just be the sound of a cracking crust, they could be spacetime itself creaking open a door. At scales 1 billion trillion times smaller than an atom, spacetime might not be smooth and serene, it could be a frothing, bubbling foam, churning with microscopic wormholes that flicker in and out of existence like bubbles in boiling water. This isn't just poetic imagery, it's the heart of quantum gravity foam theory, a radical idea suggesting that the fabric of reality is riddled with tunnels at the Planck scale, each one a fleeting shortcut through spacetime's hidden depths. The math behind this is both elegant and mind-bending. Quantum mechanics tells us that at the smallest scales, nothing is ever truly still. Virtual particles pop in and out of existence, energy fluctuates wildly, and spacetime itself becomes a turbulent sea. Some theories of quantum gravity propose that this turbulence doesn't just create random wrinkles, it weaves spacetime into a fractal-like network of wormholes, each lasting mere fractions of a second before dissolving back into the foam. Picture the universe's foundation not as a solid floor, but as a swarm of fireflies, their brief flashes of light tracing paths that, if you could stitch them together, might form a bridge across the cosmos. So how do we test something so infinitesimally small? Gamma ray bursts, the universe's most violent explosions, could hold the key. When these jets of high-energy radiation streak across the cosmos, they're essentially probing spacetime's structure at the quantum level. If spacetime is indeed a seething foam of wormholes, the burst's photons wouldn't all travel the same path. Some might take shortcuts through microscopic tunnels, arriving at Earth a hair sooner than their counterparts. The difference would be vanishingly small, a few milliseconds over billions of light years, but modern telescopes like the Fermi Gamma Ray Space Telescope are sensitive enough to catch these anomalies. In 2014, researchers analyzing gamma ray burst data reported tantalizing hints of this very effect. Some high-energy photons seemed to outpace their lower-energy siblings in ways that couldn't be explained by conventional physics. The leading explanation, quantum foam's wormholes might be subtly altering the photons' paths like stones diverting a stream. It's not conclusive proof yet. But as telescopes grow sharper and AI sifts through petabytes of cosmic data, we might soon spot the unmistakable fingerprint of spacetime's bubbling underbelly. The implications rewrite our understanding of reality. If wormholes exist at the Planck scale, they could be the universe's original internet, a chaotic, self-assembling network through which quantum information hops instantly, bypassing the speed of light. Black holes might not be cosmic dead ends, but nodes in this vast web, their singularities tangled with wormholes like submerged roots. Even time itself could emerge from this foam, with causality woven from threads of microscopic bridges. But here's the most electrifying thought. If we can map this foam, we might learn to navigate it. Advanced civilizations could exploit these natural wormholes, stabilizing them not with exotic matter, but by synchronizing their quantum fluctuations, turning the universe's noise into a symphony of shortcuts. The key to interstellar travel might not lie in building rockets, but in listening to spacetime's whispers, where every fleeting bubble hums with the promise of a path unseen. So the next time you gaze at the night sky, remember, the vast distances between stars might be an illusion. Beneath the quiet surface of reality, the universe could be stitching itself together, one microscopic wormhole at a time. The black hole firewall paradox isn't just a puzzle, it might be the universe's most violent wormhole factory. Picture the event horizon of a black hole not as a serene boundary, but as a searing wall of energy wherein falling matter is obliterated in an instant. This firewall hypothesis was born from a clash between quantum mechanics and general relativity, a cosmic tug of war over whether information can truly vanish. But what if the firewall isn't the end of the story? What if it's the moment matter gets stripped down to its quantum essence and teleported, reassembled somewhere else through a wormhole forged in the inferno? Here's how the pieces fit together. When an object crosses the event horizon, general relativity says it should feel nothing special, a principle called no drama. But quantum mechanics insists that information can't be lost, meaning the object's quantum state must be preserved somewhere. The firewall was proposed as a brutal solution, the object burns up at the horizon, its information encoded in the radiation. Yet this creates another problem. Why would spacetime suddenly turn into a blazing death trap? Wormholes offer an elegant fix. As matter nears the horizon, extreme tidal forces could stretch spacetime so thin that a microscopic wormhole forms, threading through the firewall like a needle through a flame. The matter isn't destroyed, it's scrambled into quantum bits and ejected through this tunnel, emerging elsewhere as Hawking radiation or even in another universe entirely. The math behind this is as beautiful as it is bizarre. In 2013, physicists Juan Maldacena and Leonard Susskind proposed that entangled black holes connected by wormholes could resolve the information paradox. Their ER=EPR conjecture suggests that every particle falling into a black hole becomes entangled with its Hawking radiation counterpart, and that entanglement is the wormhole. The firewall, then, isn't a wall at all. It's a quantum transfer point where matter gets disassembled and routed through a spacetime shortcut. Think of it like a cosmic fax machine. The original document is shredded, but the information gets transmitted perfectly to another location where it's reprinted atom by atom. Observational clues might already exist. When black holes merge, the gravitational waves they produce sometimes show unexpected echoes in the data ripples that shouldn't be there if the event horizons are smooth and featureless. Some theorists argue these echoes could be the signatures of firewalls, or more precisely, the wormholes flickering into existence as matter hits the horizon. Future gravitational wave detectors with even finer sensitivity could catch these whispers, turning a theoretical paradox into observable physics. But the real kicker: if firewalls spawn wormholes, then black holes aren't cosmic dead ends, they're transformers, recycling matter into new forms across spacetime. A star that falls into one might not be gone. It could be reconstituted elsewhere, its atoms rearranged but its quantum identity intact. Advanced civilizations might even harness this process, using controlled collisions to open temporary wormholes for communication or travel. After all, if the universe insists on preserving information, it might have built the ultimate escape hatch into every black hole's heart, not a fiery end, but a door waiting to be walked through. So the next time you hear about a black hole's destructive power, remember, destruction might be an illusion. The universe doesn't erase, it redirects, and the firewall could be its most ingenious cloak for the greatest magic trick of all: teleportation by way of self-correcting spacetime. String theory paints our universe not as an island, but as a membrane or brain floating in a higher dimensional expanse called the bulk. Now imagine another brain drifting silently through this cosmic void, its vibrations humming with the laws of an entirely different reality. When these brains collide, the energy released could birth not just a new universe, but something far stranger. Wormholes threaded like stitches between the two worlds, remnants of the moment they touched. This isn't pure speculation. The ekpyrotic model, a radical alternative to the Big Bang theory, suggests our universe began when two brains smashed together in the bulk, an event so violent it ignited the cosmic fireball we now call the Big Bang. But if brains can collide once, they can collide again, and each collision might leave behind spacetime defects, wormholes tunneling through the bulk like scars. These wouldn't be the smooth, symmetrical bridges of sci-fi. They'd be twisted, asymmetrical, shaped by the chaotic dance of the colliding brains, their mouths anchored to points where the membranes briefly fused. The physics gets dizzying. String theory posits that brains aren't static, they ripple and warp like sheets in the wind. When two brains graze each other, their gravitational interactions could stretch spacetime into temporary bridges. Some models suggest these wormholes would be fleeting, snapping shut as the brains rebound. Others propose that if the collision imparts enough spin, the wormholes might stabilize, their throats lined with exotic matter from the brain boundary itself. Picture it like two soap bubbles merging. For an instant, their surfaces fuse into a tunnel before separating, but if the conditions are just right, that tunnel might persist, linking the bubbles long after they drift apart. The echoes of such an event could be hiding in plain sight. If the Big Bang was indeed a brain collision, the cosmic microwave background might bear fingerprints of primordial wormholes, subtle temperature variations, or polarization patterns shaped by spacetime's violent stretching. Some theorists even speculate that dark matter's mysterious distribution could be traced to these ancient tunnels, their gravitational influence warping the cosmos like invisible hands pressing on clay. And here's the wildest twist: if brains collide cyclically, as some string theory models suggest, then wormholes might not just be relics of the last collision, they could be previews of the next. Advanced civilizations, aware of the impending collision, might use these tunnels as escape routes, fleeing their doomed brain for another before the cosmic reset. It's a haunting thought. The universe's first wormholes could also be its last, stitching together not just space, but time itself, bridges between cosmic lifetimes we've yet to imagine. So the next time you hear about the Big Bang, consider this. It might not have been the beginning, but a rebirth, and the wormholes we're searching for could be remnants of a universe that came before, whispering through the bulk like echoes in a cathedral of dimensions. Time crystals sound like something ripped from a sci-fi epic, structures that pulse and cycle without energy, breaking the traditional rules of thermodynamics. But these bizarre quantum states are very real, first theorized in 2012 and later created in labs using chains of ions or diamond defects. Now, imagine harnessing their endless clockwork motion to power something even more extraordinary: wormholes holding themselves open against gravity's relentless pull. This isn't fantasy, it's a serious theory gaining traction, where the universe's most enigmatic phenomena could collide to rewrite the laws of physics. At their core, time crystals are systems that oscillate between states without losing energy, like a pendulum that never stops swinging. Unlike ordinary crystals, which repeat their structure in space, time crystals repeat in time, their atoms flipping spin directions predictably forever without friction or decay. In 2017, researchers at Harvard and the University of Maryland brought these theoretical curiosities to life, using lasers to nudge ytterbium atoms into this paradoxical dance. The implications were staggering. Here was a new phase of matter, one that could potentially cheat entropy itself. Now apply that to wormholes. One of the biggest hurdles to stabilizing a traversable wormhole is the need for negative energy, an exotic substance to prop the tunnel open against collapse. But time crystals offer a loophole. Their perpetual motion could, in theory, generate a form of dynamic stabilization, where the wormhole's throat pulses in sync with the crystal's rhythm. Picture a doorway made of sliding panels. If the panels move fast enough, anything passing through wouldn't notice they're never all open at once. A time crystal's oscillations might do the same for spacetime, creating an effective negative energy effect without requiring impossible amounts of exotic matter. Lab experiments are already hinting at the possibilities. In 2021, a team at Stanford entangled a time crystal with a quantum processor, observing how its rhythmic pulses could influence entangled particles across distances. The math suggested something eerie. The crystal's behavior mimicked the equations describing a wormhole's throat fluctuating in sync with an external energy source. It wasn't a wormhole, of course, but it proved that time crystals can imprint their order onto quantum systems in ways that eerily resemble spacetime bridges. Thermodynamics throws another curveball. Normally, any machine that powers a wormhole would need infinite energy, violating the second law. But time crystals exist outside equilibrium, their endless cycles sidestepping entropy's grasp. Some models suggest that if a crystal's oscillations were tuned to a wormhole's natural frequency, the system could reach a bizarre steady state, neither gaining nor losing energy, just persisting like a cosmic engine idling forever. It's the ultimate bootstrap paradox, a wormhole stabilized by a structure that itself defies decay. The wildest implication: If time crystals can stabilize wormholes, they might already be doing so naturally. The early universe's extreme conditions could have birthed primordial time crystals, their pulses freezing into spacetime's fabric like cosmic metronomes. Advanced civilizations might not need to build wormhole engines. They could simply pinpoint these natural time anchors, tapping into rhythms older than stars. Or perhaps they'd cultivate time crystals artificially, growing them in quantum furnaces to weave wormholes like threads on a loom. So while time crystals began as a curiosity, they might end up as the universe's most elegant loophole, a way to hold open doors between worlds without burning a single star for fuel. The lesson: sometimes to bend the rules, you don't break them. You dance to a rhythm they've forgotten. Magnetic monopoles, those elusive, hypothetical particles with a single magnetic pole, might do more than just tidy up Maxwell's equations. If they exist, they could be nature's ultimate seamstresses, stitching wormholes into the fabric of spacetime itself. Picture a universe where every magnetic monopole doesn't just carry a north or south charge, but drags behind it an invisible thread of twisted spacetime, a filament so fine it's practically a wormhole in waiting. This idea isn't just speculative fantasy, it's grounded in the same math that first predicted monopoles over a century ago, and it could rewrite how we think about cosmic shortcuts. The story starts with Paul Dirac's groundbreaking work in 1931. He showed that if even a single magnetic monopole existed anywhere in the universe, it would explain why electric charge comes in neat, discrete packets, a phenomenon called charge quantization. The key lies in the monopole's gravitational footprint. As it moves, its singular magnetic field would warp spacetime in a unique way, creating a swirling vortex of curvature around it. Now fast forward to grand unified theories, which suggest monopoles should have formed in abundance during the universe's early, high-energy phase. If so, their combined gravitational effects could have woven spacetime into a labyrinth of microscopic wormholes, like pins holding folds in a cosmic tapestry. Here's where it gets wild. These monopole wormholes wouldn't be the symmetrical, engineered tunnels of sci-fi. They'd be messy, asymmetrical, and fleeting, more like quantum knots than bridges. But under the right conditions, they might stabilize. Simulations from string theory suggest that when monopoles pair up, north and south, their opposing magnetic fields could stretch spacetime between them into a stable throat, a wormhole held open by the tension of their attraction. It's as if the universe handed us a recipe for wormholes with monopoles as the key ingredient. The real kicker: we might already have evidence. Cosmic rays, high-energy particles raining down from space, sometimes carry signatures that defy explanation. In 2020, the ANITA experiment detected anomalous particles skimming up through Antarctica, as if they'd traveled unimpeded through the Earth. One tantalizing explanation: they didn't go through, they went around, tunneling through a monopole-spawned wormhole. It's a long shot, but if future detectors spot more of these cosmic anomalies, we could be staring at the fingerprints of Dirac's hypothetical particles and the wormholes they left behind. So while magnetic monopoles remain undiscovered, their potential legacy is already woven into the universe's blueprint. They might be the missing link between quantum weirdness and cosmic structure, the secret architects of shortcuts we've yet to map. And if we ever find one, it won't just complete a century-old equation. It might hand us the keys to spacetime itself. Hawking radiation, the faint glow that slowly bleeds energy from black holes, is usually thought of as a one-way street, the universe's way of ensuring even the mightiest black holes eventually evaporate. But what if we could reverse the process? Picture collecting every particle of Hawking radiation emitted by a black hole, then firing it back in like cosmic buckshot. The result wouldn't just slow the black hole's demise. It could trigger a dramatic transformation, collapsing the singularity into something far stranger, a wormhole threaded through spacetime like a needle through fabric. The math behind this is as audacious as it is elegant. Hawking radiation arises when quantum fluctuations near the event horizon produce particle-antiparticle pairs. Normally, one falls in while the other escapes, carrying away energy. But if we could somehow capture every escaping particle and its antimatter twin, then perfectly reverse their trajectories, we'd effectively inject energy back into the black hole. Calculations from quantum field theory suggest that under precise conditions, this influx could destabilize the singularity's gravitational grip, causing it to rebound into a Planck star, a hyper-dense remnant theorized to sit at the heart of some wormholes. Energy budgets make this a cosmic-scale challenge. A stellar mass black hole emits Hawking radiation at a feeble 10 to the minus 29 watts, less than the energy needed to power a light bulb for a femtosecond. Collecting and reversing this would require unfathomable precision, like trying to reassemble a shattered wine glass from the sound of its breaking. But for a microscopic black hole, the kind that might have formed in the early universe's chaos, the numbers flip. These tiny beasts emit radiation at blistering intensities, their evaporation a fireworks finale of particles. Reverse that cascade, and the energy density could be enough to tip the black hole into a wormhole state, its singularity stretching into a tunnel. Lab experiments are already probing the edges of this idea. In 2021, researchers at the Technion Israel Institute of Technology simulated Hawking radiation in a water tank using waves to mimic particle pairs. By carefully tuning the system, they managed to reverse the equivalent of radiation, causing their black hole analog to temporarily restabilize. It wasn't a true wormhole, of course, but the principles aligned eerily with the math. Meanwhile, quantum computers are tackling related problems like how information scrambled in Hawking radiation might be unscrambled and fed back into a simulated black hole, a first step toward testing reversal on a chip. The ultimate implication: if reversing Hawking radiation can morph a black hole into a wormhole, then the universe might be seeded with these tunnels already. Primordial black holes, those hypothetical relics from the Big Bang, could have evaporated long ago, but not before a fraction of their radiation was twisted back by chaotic spacetime conditions, birthing wormholes that still linger today. Advanced civilizations wouldn't need to build wormholes from scratch. They'd just need to find these cosmic orphans and wake them up with a carefully aimed pulse of energy, like reviving a dormant engine with a jump start. And here's the wildest thought. If time runs backward inside a rebounding black hole, as some quantum gravity models suggest, then these Hawking reversed wormholes might not just bridge space, they could stitch together inverted timelines. A traveler stepping through might emerge not just elsewhere but elsewhere, their fate tangled in a loop where radiation's end is the wormhole's beginning. The universe loves symmetry. What evaporates away might just return in another form, woven into the fabric of reality like a hidden seam. Imagine a universe identical to ours in every way, except flipped like a reflection in a mirror. Atoms spin the opposite direction, molecules twist counterclockwise, and even time might flow backward. This isn't sci-fi. It's the mirror matter hypothesis, a legitimate theory suggesting a hidden twin cosmos lurking just beyond our perception. And the key to unlocking this parallel reality might be the universe's stealthiest particles, sterile neutrinos, ghostly travelers that could open wormholes between worlds with just a flick of their quantum spin. Sterile neutrinos are the oddballs of the particle zoo. Unlike regular neutrinos, which barely interact with matter, sterile neutrinos don't interact at all except through gravity. They're shadows of shadows, passing through planets and stars as if they weren't there. But here's the twist. Some theories suggest these elusive particles might not just be passive observers, they could be cosmic locksmiths, capable of twisting space-time into bridges between our universe and its mirror twin. The magic lies in chirality, a property that determines how particles spin. Our universe's matter is left-handed, neutrinos spin counter-clockwise relative to their motion. But mirror matter would be right-handed, spinning the opposite way. sterile neutrinos uniquely can flip between these states in high-energy environments like near a black hole or during a supernova. This flipping could create a chirality vortex, a swirling imbalance in spacetime's fabric. Picture a whirlpool where the water reverses direction mid-spin. The turbulence at that boundary might tear open a microscopic wormhole, a fleeting tunnel to the mirror universe. The math behind this is startlingly elegant. Quantum field theory shows that when sterile neutrinos oscillate between chiral states, they emit gravitational waves at frequencies beyond anything we've detected. These waves wouldn't just ripple spacetime, they'd twist it like wringing out a wet towel. If the waves intersect at just the right angle, the twisting could pinch spacetime into a Klein bottle, a shape where inside and outside merge, creating a passage between mirror realities. Experiments might already be catching whispers of this phenomenon. The Anita telescope floating over Antarctica has detected anomalous neutrino-like particles coming up from the Earth as if they'd tunneled through the planet unimpeded. One explanation, these weren't ordinary neutrinos but sterile neutrinos that briefly dipped into the mirror universe, bypassing matter entirely. Even more tantalizing, certain gamma-ray bursts show energy signatures that don't match any known particle decay, unless you account for a fraction of energy leaking into a mirror dimension through microscopic wormholes. The implications rewrite the rules of reality. If sterile neutrinos can open wormholes to a mirror universe, then dark matter, the invisible glue holding galaxies together, might not be exotic particles at all. It could be mirror stars and planets, their gravity bleeding through wormholes we've yet to map. Advanced civilizations wouldn't need warp drives. They'd just need to coax sterile neutrinos into singing the right quantum tune, harmonizing spacetime into a doorway. And then there's the existential kicker. If mirror matter exists, it could solve one of physics' greatest mysteries: why our universe is made of matter and not antimatter. The Big Bang should have created equal amounts of both, leading to mutual annihilation. But if some matter fled through primordial neutrino wormholes into the mirror realm, it would leave our universe lopsided, dominant, and alive. The mirror universe might not just be our twin, it could be the reason we exist at all. So the next time a neutrino detector blips, pay attention. That faint signal might not just be a ghostly particle passing through. It could be a knock on the door from a universe where everything spins the other way, waiting for us to twist spacetime just right and answer. Quantum Darwinism turns the observer effect into a cosmic sculptor, where conscious attention doesn't just measure reality, but shapes it into existence. Imagine every act of observation as a chisel striking spacetime, carving away unstable quantum possibilities until only the most robust structures remain. Now take that idea further. What if wormholes aren't accidental wrinkles in the cosmos, but the universe's preferred pathways, etched into permanence by countless observers over billions of years? This theory starts with a radical reimagining of quantum mechanics. In the traditional Copenhagen interpretation, observing a quantum system collapses its wave function, forcing fuzzy probabilities into concrete states. Quantum Darwinism adds a twist. Not all outcomes are equally likely to survive. Just as natural selection favors traits that aid reproduction, quantum states that withstand scrutiny get reinforced while fragile configurations fade away. Apply this to spacetime itself and you get a startling possibility. Wormholes could be the fittest spacetime structures, their stability honed by relentless observation from particles, stars, even conscious beings. Think of the early universe as a quantum soup, bubbling with fleeting wormholes that wink in and out of existence. Most vanish instantly, victims of quantum fluctuations. But a rare few find themselves in the right place at the right time, perhaps near a cluster of particles whose interactions observe spacetime geometry. Each measurement acts like a vote, reinforcing the wormhole structure until it becomes a permanent fixture. Over eons, this Darwinian process could weave a tapestry of preferred pathways through spacetime, their survival ensured by the very act of being used. Evidence might lurk in quantum entanglement experiments. When particles entangle across vast distances, their correlation suggests a deeper connection, one that could be mediated by microscopic wormholes stabilized through observation. In 2023, a team at the University of Chicago noticed something peculiar. Entangled photons seem to choose their alignment faster when observed by multiple detectors, as if the act of measurement was tightening an invisible thread between them. Could that thread be a spacetime bridge hardened into reality by collective attention? The implications rewrite the rules of exploration. If wormholes exist because observers sustain them, then traversing one might require more than exotic matter. It could demand participation. Advanced civilizations might not just map wormholes, they'd cultivate them, using quantum sensors to continually reinforce the tunnels they rely on. A wormhole left unattended could fray like an unused muscle, dissolving back into the quantum foam. The universe's shortcuts wouldn't be freeways, they'd be living structures, thriving only where life notices them. And here's the existential kicker. If conscious observation shapes spacetime, then the first wormholes might have been born from the universe observing itself. Before stars or planets, quantum fluctuations in the early cosmos could have acted as proto-observers, their interactions collapsing spacetime into bridges that outlasted their creators. We might be living in a cosmos where reality is literally built by looking, and the oldest wormholes are the scars of a universe learning to see. What if the universe isn't just aware? What if it's listening? Panpsychism, the radical idea that consciousness isn't confined to brains but is a fundamental property of reality, takes this even further. Imagine every thought, every moment of awareness as a ripple in spacetime, subtly bending the fabric of the cosmos. Under this view, wormholes might not be accidental cosmic quirks. They could be the universe's response to a chorus of conscious observation, a way to knit together the places where minds have pressed hardest against the boundaries of reality. This isn't just poetic speculation. Sir Roger Penrose's Or theory proposes that consciousness arises from quantum vibrations in microtubules, tiny structures inside our brain cells. These vibrations, Penrose suggests, don't just occur in spacetime, they interact with it, collapsing quantum possibilities into concrete experience. If true, then a sufficiently focused collective consciousness, say, billions of humans meditating on the same idea, or even a single mind under the influence of psychedelics, might warp spacetime in measurable ways. Picture a million fingers pressing against the same point on a trampoline. Eventually, the fabric would dip far enough to touch another surface. In this case, the surface might be another time, another dimension, or even another universe. Anecdotes from psychedelic experiences add eerie weight to the idea. Users of DMT, a compound that catapults the brain into hyperdimensional states, frequently report encounters with entities and landscapes that feel more real than reality. Stranger still, these descriptions often overlap, as if independent minds are tapping into the same non-local space. Could these shared visions be glimpses through temporary wormholes, forged by the sheer intensity of consciousness under the compound's influence? Even more provocative, near-death experiences where individuals clinically dead report traversing tunnels of light. Might these be subjective interpretations of spacetime bridges, opened by a brain teetering on the quantum edge? The math hints at plausibility. Quantum entanglement shows that observation affects reality, and if consciousness is a form of quantum observation scaled up, its cumulative effects could be profound. Some models suggest that coherent brain activity, like that achieved in deep meditation or under psychedelics, might generate microcurvatures in space-time, tiny wormholes connecting individual minds into a larger network. It's as if the universe has a hidden backchannel, accessible only when consciousness vibrates at the right frequency. the implications rewrite the rules of existence. If collective thought can bend spacetime, then ancient ritual stone circles, chanting, ayahuasca ceremonies might have been unwitting experiments in wormhole engineering. Advanced civilizations wouldn't need metal stargates. They'd use synchronized consciousness as their engine, folding space not with machinery but with focused awareness. Even our modern internet, a digital hive mind, could be subtly reshaping reality's geometry, weaving threads we don't yet know how to see. And then there's the haunting question: if consciousness creates wormholes, what's on the other side? Perhaps the universe's first travelers weren't beings with ships, but minds with enough intensity to punch through the veil, leaving behind bridges we're only beginning to sense. The cosmos might not just be alive, it might be waiting for us to notice how deeply we're entangled in its fabric. Dark energy isn't just a mysterious force pushing the universe apart. It could be a churning ocean of quantum foam, its waves occasionally cresting into wormholes. Picture the cosmos not as a smooth, expanding sheet, but as a turbulent sea where dark energy's fluctuations ripple through spacetime like storm swells. In the chaos of those peaks and troughs, the fabric of reality might twist into temporary tunnels, connecting distant points like bubbles fusing in a breaking wave. These wouldn't be the grand, stable wormholes of science fiction. They'd be wild, ephemeral things born from the universe's underlying restlessness. The math behind this is as mesmerizing as the metaphor. Dark energy is often modeled as a cosmological constant, a uniform, unchanging background energy. But what if it's actually a dynamic field, its strength waxing and waning like the tide? Quantum field theory allows for this possibility, with fluctuations so intense they could warp spacetime into microscopic wormholes. Think of it like a rubber sheet being shaken violently. Where the vibrations overlap, tiny tears might form, stitching the sheet back together in unexpected ways. These wormholes wouldn't last long, just trillionths of a second, but in the quantum realm, that's enough time for information or even particles to slip through. Observational clues might already be hiding in the cosmic microwave background. If dark energy's fluctuations were strong enough to spawn wormholes in the early universe, their gravitational echoes could have left faint, circular imprints in the CMB's temperature patterns. Some researchers argue that certain anomalies, unexplained cold spots or odd symmetries, could be the fingerprints of these ancient spacetime bubbles. Future telescopes like the Simons Observatory could scan for these signatures with unprecedented precision, turning what's now a compelling theory into hard evidence. The implications rewrite our understanding of cosmic expansion. If dark energy's fluctuations create wormholes, then the universe isn't just stretching, it's bubbling with hidden connections. Galaxies drifting apart in one region might be subtly linked to others through these quantum tunnels, like distant boats tied together by invisible ropes. Even stranger, if these wormholes thread through higher dimensions, they could explain why dark energy's effects seem so uniform. What looks like a smooth, relentless push from our 3D perspective might actually be the shadow of a hyperdimensional knot, its true shape hidden from view. But here's the most tantalizing thought. If dark energy's fluctuations birthed wormholes in the past, they might still be forming today. The vacuum of space isn't truly empty. It's a seething quantum soup where particles flicker in and out of existence. Under the right conditions, these quantum bubbles could intersect with dark energy's ripples, birthing wormholes in the void. Advanced civilizations might have already learned to harness this process, coaxing spacetime into forming bridges where nature alone would leave only fleeting whispers. So the next time you hear about dark energy's role in cosmic expansion, remember, it might not just be pushing the universe apart. It could be weaving it together, one quantum tunnel at a time. What if gravity isn't a fundamental force at all, not a tug between masses, but a side effect of chaos itself? Eric Verland's entropic gravity theory turns physics on its head by suggesting gravity emerges from the universe's relentless drive toward disorder. Now take that idea further. What if wormholes aren't just cosmic shortcuts, but the ultimate expression of entropy, spacetime's way of maximizing chaos by forging paths where information can spread fastest? Think of the universe as a vast, tangled network where every particle, every bit of energy carries information. Entropy, in this view, isn't just about disorder. It's about the number of ways that information can be arranged. Verlin's theory proposes that gravity arises from this information scramble, like the way heat disperses in a room not because of some invisible force, but because molecules seek the most probable configurations. Apply this to spacetime and you get a startling possibility. Wormholes could be natural dislocations where entropy reaches its peak, warping the fabric of reality into bridges that let information flow with minimal resistance. Visualize it like ice cracking under pressure. When stress builds, the crystalline structure buckles at weak points, forming fractures that relieve the tension. In entropic gravity, spacetime behaves similarly where information density becomes too chaotic. Spacetime cracks into a wormhole, creating a shortcut that restores equilibrium. These wouldn't be smooth, engineered tunnels, but jagged, fractal-like conduits shaped by the raw statistics of entropy. A black hole's event horizon, for instance, might not just trap information, it could funnel it through a wormhole to somewhere entropy can run even wilder. The math behind this is surprisingly elegant. In Verlin's framework, gravity's strength depends on how much information is hidden from a given observer, a concept called holographic entropy. Wormholes, it turns out, minimize this hidden information, effectively erasing the distance between 2 points in the most entropically efficient way possible. It's as if spacetime, when faced with the computational overload of tracking too many entangled states, opts to zip faraway regions together, reducing the cosmic ledger's complexity. This could explain why wormholes appear in quantum gravity models like ER=EPR. They're not just geometric tricks, but entropy's ultimate optimization. Clues might lie in the cosmic microwave background. If early universe wormholes formed as entropy relief valves, their imprint could linger in the CMB's temperature variations, subtle, filamentary patterns where information once gushed through spacetime's cracks. Future telescopes hunting for these signatures could find not just evidence of wormholes, but proof that gravity itself is an emergent illusion, woven from the universe's desperate need to forget. And here's the existential kicker. If entropic gravity is real, traversable wormholes might not require exotic matter or negative energy. They'd emerge naturally anywhere information flow gets bottlenecked, like turbulence smoothing into a whirlpool. Advanced civilizations wouldn't build wormholes, they'd coax them into existence by engineering chaos, manipulating entropy gradients to make spacetime fold itself. The ultimate cosmic hack might not be bending the laws of physics, but convincing the universe it's the most disordered path forward. So the next time you feel gravity's pull, consider this: you're not falling toward a mass. You're sliding down a gradient of cosmic forgetfulness, and somewhere, a wormhole might be forming in the chaos you leave behind. The universe's first wormhole might not have been a tunnel for matter or energy. It could have been a sprawling, self-correcting quantum computer, its logic gates etched into the very fabric of spacetime. Picture this: a wormhole's twin event horizons acting like cosmic hard drives, encoding quantum bits in the fluctuations of their surfaces. Every particle that ever brushed against the horizon wouldn't just vanish, it'd imprint its quantum state onto the boundary, like a fingerprint pressed into holographic film. These imprints wouldn't just sit there, they'd interact, entangle, and compute, weaving a tapestry of information processing that could solve problems no classical computer ever could. This idea springs from the holographic principle, which suggests that all the information in a volume of space, every star, every atom, can be encoded on its boundary, like a 3D movie projected from a 2D screen. Apply that to a wormhole, and its event horizons become the ultimate processing surfaces. Qubits could be stored in the microscopic peaks and troughs of spacetime itself, their states flipped by the gravitational dance of virtual particles at the horizon's edge. Calculations wouldn't happen in the wormhole's interior, but on its skin, where quantum entanglement stitches together a lattice of logic gates spanning light years. It's as if the universe's first computer wasn't built, it was grown, a natural byproduct of spacetime's deepest geometry. The computational power of such a system would be staggering. Unlike our fragile quantum bits, which decohere at the slightest disturbance, a holographic wormhole's qubits would be stabilized by the horizon's sheer gravitational might. Error correction built in. The no-hair theorem ensures that only certain quantum states can persist on the horizon, automatically filtering out noise. Need more processing power? Just feed the wormhole more mass, expanding its surface area and qubit capacity. A black hole the size of our solar system could host more qubits than there are particles in the observable universe, all humming in perfect, non-local harmony. Here's where it gets wild. This cosmic computer might still be running. If primordial wormholes formed in the early universe, some could have survived, their event horizons quietly crunching quantum algorithms in the dark. We wouldn't see them, not directly, but their output might be hiding in plain sight. Certain patterns in the cosmic microwave background or anomalies in the distribution of dark matter could be the remnants of calculations performed 14 billion years ago, their answers etched into the structure of reality itself. The universe's first hard drive might have left its data imprinted on the cosmos, waiting for us to crack the code. And then there's the ultimate twist. If wormholes compute, they might not just process information, they could create it. Some theories suggest that the universe's laws of physics aren't fundamental, but emergent, like the rules of a game emerging from its code. A holographic wormhole computer could be that coder, its endless cycles of entanglement and measurement birthing the very constants we take for granted. The speed of light, the strength of gravity, these might not be fixed numbers, but variables in a cosmic program still running in the background, its output the reality we inhabit. So the next time you boot up your laptop, consider this. The universe might have been running its own quantum algorithms since the dawn of time, not on silicon but on spacetime itself. The first computer wasn't human. It was a wormhole humming with the universe's oldest computations, its answers written in the stars. What if the universe isn't a cosmic accident or divine creation, but an unfathomably complex simulation? And wormholes aren't natural phenomena but glitches in the code. This theory takes the simulation hypothesis and cranks it to 11, proposing that spacetime's shortcuts aren't features of reality, but bugs, backdoors left in the cosmic software, either by design or oversight. And the evidence might be hiding in plain sight, disguised as inexplicable anomalies scientists politely call rendering artifacts. Think of the universe as a vast video game with spacetime as its engine. Even the most polished games have flaws, textures that don't load properly, objects that clip through walls, or areas where the physics engine breaks down. Now imagine similar quirks at a cosmic scale, particles that teleport inexplicably, regions where gravity briefly inverts, or celestial objects that vanish and reappear light years away. These wouldn't just be oddities, they'd be the simulation struggling to render reality consistently, its code buckling under the processing load. Wormholes, in this view, are spacetime's version of a corrupted save file, places where the universe's algorithms short-cut their own calculations to keep things running. Some of these glitches might already be in the scientific record. Take quantum tunneling, where particles seemingly vanish from one location and materialize in another without crossing the space in between. It's a well-documented phenomenon, but from a simulation perspective, it looks suspiciously like a rendering optimization. The universe's processor skipping unnecessary calculations to save resources. Even stranger are cosmic rays with energies so high they should interact with the cosmic microwave background and dissipate before reaching Earth, yet they don't. Could these ultra-high-energy particles be bypassing the usual physics engine entirely, slipping through spacetime's debug mode? Then there's the Mandela effect, those eerie collective false memories where large groups swear historical details have changed. While often dismissed as psychological quirks, simulation theorists propose an alternative. These could be literal patches to the universe's code, updates rolled out so hastily they leave inconsistencies in the rendering. If spacetime itself is mutable under the hood, wormholes might not just be transportation devices, they could be the universe's undo function, stitching together alternate versions of reality when the simulation corrects itself. The most chilling implication: if wormholes are backdoors, someone or something might be using them. Just as programmers leave Easter eggs in games, the architects of our simulated reality could have embedded these tunnels as cheat codes, accessible only to those who know the right commands. Ancient myths of gods descending through celestial gates, modern UFO sightings near gravitational anomalies, even reports of time slips. What if these are glimpses of entities navigating the simulation's debug menu, hopping between layers of the cosmic stack with terrifying ease? But here's the twist: if wormholes are glitches, exploiting them could trigger the universe's antivirus protocols. Early attempts to stabilize a wormhole might appear successful until the simulation's error correction routines kick in, rewriting local physics to seal the breach. The Fermi paradox gets a grim new angle. Perhaps advanced civilizations don't colonize the stars because they tried hacking the simulation and got patched out. So the next time you hear about a physics-defying anomaly, consider this. It might not be a breakthrough waiting for a Nobel Prize. It could be the universe's source code showing through, and the first wormhole travelers might not be astronauts but rogue players who cracked the game. From Boltzmann brains hallucinating wormholes into existence, to cosmic strings stitching spacetime into a labyrinth of shortcuts, each theory we've explored doesn't just bend the rules of reality, it snaps them in half. Picture a universe where black holes are backdoors, where consciousness itself warps spacetime, or where dark energy's chaos weaves hidden tunnels between galaxies. These aren't just sci-fi fantasies, they're legitimate frontiers of physics, each one peeling back another layer of the cosmos's deepest secrets. The sheer audacity of these ideas forces us to confront a humbling truth. We might barely understand the stage we're standing on, let alone the script. Take the holographic principle. What if everything we see, touch, and are is just a projection from a 2D surface at the edge of reality? Or vacuum decay, where a single quantum misstep could rewrite physics itself, leaving wormholes as emergency exits in its wake. Even the simulation hypothesis, where glitches in the cosmic code might be the only way to glimpse the universe's true nature, challenges us to question whether reality is just a user interface. These theories don't just speculate about wormholes, they redefine what the universe is, turning pillars of science into questions we're only beginning to ask. So now it's your turn. Which idea shattered your expectations? Did the thought of neutrinos punching holes in spacetime leave you reeling? Or did the notion of time crystals powering eternal wormholes spark your imagination? Drop your favorites in the comments. We're all cosmic detectives here, piecing together the universe's wildest blueprints. And if your brain's still buzzing from these mind-bending possibilities, hit subscribe. The universe has more mysteries waiting, and we're just getting started.